Hi, everyone, and welcome to the program today. My name is Paul Bemis. I'm the president of Applied Math Modeling. I'll be doing the broadcast for you today. All right, so let's get started. We're talking about modeling external heat flows in data center designs. A little bit about our company, Applied Math Modeling. Most of you know us at this point. We've been around for quite some time. We are a partner of the Ansys Corporation. We came out of that corporation where I was a senior executive for many years, responsible for their products. And this one we built in a bit of a skunk works while I was there and agreed to take it private. A little small for them as a big corporation. So we are a partner of theirs now, and we deliver this solution in a SaaS model, software as a service, which is really quite nice, particularly for this kind of analysis we're doing today, because it tends to be computationally intensive and take some more time to solve than internal flow models. We are experts in the field of CFD, sales, development, support. We do consulting as well. We can build these models and run them for you if you choose, or you can use our CoolSim software and do it yourself. Either is effective. So let's talk about modeling external heat. We've done a fairly good job inside the data center over the past 20 years. Things like hot aisle, cold aisle, containment, hot aisle or cold aisle containment, variable speed fans have all contributed to the goal of getting the heat out of the building, out of the room. However, it's now outside. You've got a bunch of heat outside. And of course, given the cost of land and space, the architects typically, I don't want to single them out, but it's often a result that you have these locations outside the building that are made up of a bunch of heat exchangers. They could be chillers, they could be condensers, they could be whatever, but at the end of the day, we've got to get that heat out of the building and pump it into the outdoor air. In addition, there's also the issue of external generators. So one of the issues that we always face is what happens when the power fails. The IT servers themselves are backed up with battery, but eventually you've got to get that diesel generator up and running unless you have a fuel cell or something, which is still a little unusual. Diesel is still the thing people use the most, these big V16 diesel generators. And guess what? They dump a bunch of heat, and they have a very hot exhaust, 900 degrees Fahrenheit coming out of the top of them. So you need to be sensitive to the fact that under a prevailing wind condition, there is some probability that that heat gets mixed up with your heat exchangers, which are actually often co-located, causing all kinds of issues that we're going to talk about today. And what happens is if the cooling system gets warm inlet temps, if the temperature coming into the heat rejection system, the condenser itself, the heat exchanger, gets too high, then their cooling capacity drops off non-linearly. It's quite fast. So cooling capacity can be diminished if the heat from anywhere gets into the intake of these devices. So that's what we're going to talk about today. Now, an example here is what you would normally see as a heat exchanger structure. This is just representative. You see over here, I've clipped one out. They all sort of look like this. Whether they're chillers or condensers, they look like this. Now, a chiller will have a box over here where the compressor sits, but it still has a big long array of these. And the more of these, the better, because it's trying to dump heat to the atmosphere. And if you don't have to compress it, you can save a lot of money. So they use a lot of these. These are air to, water, typically water to air heat exchangers. They don't have to be water. They can be something else. But there's certainly air on the outside, and they're dumping heat up through this vein on both sides and out through the top. So it's important that you know the physical diameter of this, because you're going to build these. I'm going to teach you how to build these, and what the physical characteristics are. Most importantly, mass flow rate and delta T. How much heat are you dumping? So remember that the second equation of thermodynamics for convective heat transfer is that heat is equal to mass flow rate times specific heat of air times delta T. So it's these three elements, heat, mass flow, and delta T, assuming the density remains relatively constant, which can vary, by the way, depending on temperature, that determines how much heat these devices can reject. The way we represent these in CoolSim is to use, we've generalized the PDU. We used to have a PDU little entity or object up here. We called it a PD, power distribution unit, and we use that inside the room usually. Now the room's gotten much bigger, and we're going to use it outside. The room is effectively the domain now. You're setting the domain, sometimes called a bounding box, for the volume that you're going to put your building in. So instead of putting servers in the room, we're going to put buildings in the room, quote unquote. The way we do heat exchangers is this same little structure. This is called, we call it an HDU, and fortunately enough, it has, guess what? Heat load and delta T, which results in flow rate. So these two parameters, heat load and delta T, and all you simply do is take the maximum capacity of the device that you have. So take this device, if this thing dumps 400 kilowatts max heat load, then divide it by, in this case, 8, and set each one of these to dump 1/8 of that total. They'll also give you mass flow rate. If they give you maximum mass flow rate for the whole set, then of course divide it by 8, give it to each one of them. They may give you delta T. If not, wiggle the delta T until you get the mass flow rate to where you want it. This is not an unusual delta T for these devices, 11 degrees. I'd like to see higher, but that's not an unusual number. Now, in order to mimic the flow, you see this is a rectangular device, and it has a bottom and a top, an inlet at the bottom and an outlet at the top. I made the block transparent in this case so you could see it, see underneath it, see how it was built. But the way that these are built is you create the inlets along the perimeter using our baffle object, and you set the baffle for some percent area open. 60 to 80 is not unusual. And then you're pulling the air up into this device and through the top. Now, it's not perfect because you see these are angular and this is flat. But in the greater scheme of things, what you're looking for is what's the approximate temperature coming into these devices. And here we're going to get the approximate temperature of that inlet of that PDU, or in this case, HDU. Now here, you would really want the temperature along these sides, but again, these are not constants, they vary, and the reason we're doing it rectilinear instead of as an angle is mesh size, mesh count. In CFD, we fill the volume with elements. We tend to fill them in CoolSim with hexes. So we're hex dominant, and if we use hexes, which are rectilinear in nature, then using a rectilinear structure will keep our mesh count low and give us fairly good results. So that's how we do it, and it works quite well. So there's a basic structure. There are a number of these that you can build, and you can build them different ways. This is one way to do it. And what I'm going to do here is I'm going to show you a couple of these using my CoolSim application. Now, whenever I do this, I run the risk of technical difficulties, so so just bear with me if something breaks. And here I've got both generators and heat exchangers. Now, there's a couple ways you can do this. If there's a lot of them, and the data center is really quite complicated with a lot of equipment, you can represent the array as a singular structure across, one HDU instead of two. So I could take the array of 8 that I just showed you and turn it into an array of 4 and get an equivalent answer. Now here, again, this would be equivalent to 2 of the earlier fan structures that I showed you, and you would therefore take the total mass flow rate and the total heat load and so forth and do it this way. This isn't too bad, and it creates a smaller mesh. We're all about the mesh because that's where it takes a lot of time. And then underneath this structure, what you do is simply, this is a baffle, and so you can see that it comes down here into that area, and you're pulling air up through. Essentially, all you want to know is what's the approximate, the average air temperature in that region. That's all you're really looking for. You want to know wherever these are placed, if anything's getting in there, if any other entrainment from an adjacent device is getting in there in terms of heat. So you set these to leak. The great thing here in CoolSim, we have leakage. The leakage here is set for 90%. You'll want to make sure that you line everything up nicely. And fortunately, we have great tools for that. So you can do close gaps in, this would be the X direction, and then close gaps in Z. And we have this nice close gaps feature that allows you to line those up nice and clean. If you're not lined up, you're going to get issues in meshing. Again, CFD is all about the mesh, getting the mesh right. We're hex dominant, and you're going to want to line things up as nicely as you can. The other nice thing about CoolSim is it allows grouping. So what you can do once you have a structure set up, like the one I just showed you, is group it. And the great thing about a group, so I've just rubber banded it, and now there's my tree of what's in it, and I can group it. And the great thing about group is that it allows you to not only Control-C, Control-V the structure, the whole entire group, but it allows you to clone it. And these are often lined up in data centers as a group or array. And this really helps the meshing to get these things lined up perfectly. So, for example, a clone is just simply a copy with offset, copy paste with offset. So here I'm going to offset it. Let's say I'll do 10 feet in the Z direction, and I'm going to put 3 of them in place. And it allows you to just lay these things out really quickly. And the beauty of that is that you can set a model up really fast by creating just the base structure, getting it the way you want, and then cloning it. And when you clone it, because I only cloned it in one axis, everything is exactly lined up perfectly, and the mesh is going to be as small as it can be without getting into trouble on that front. So now that's just one type. Here's another one here that you can use. You can use a structure like this one, which allows a little more detail. So here, the user has created a structure where there's a block at the bottom. You can ungroup this. You can take it apart. This is a block, as I showed you earlier, that they put in. You can make these devices the same height as the block, and they'll work fine. So make them coplanar. And then down below, leakage for the inlets. Okay. So that's how those structures are built in CoolSim. Let's switch to generators. Generators are another thing you're going to want to try to create and get to run. Generators are challenging because the sizing of them is quite disparate compared to the size of the domain itself, particularly the exhaust pipe. So these things tend to operate in this range. Is a 3 megawatt device, a diesel generator. You see the intakes along here, so it's pulling in air. It uses turbochargers. You can see them here. It's usually a V16 type of device. There are 2 things you need to worry about when modeling it. One is the air coming through into and out of the heat exchangers that are cooling the engine itself. The other is the diesel exhaust. And they generally don't sit like this, of course, in the outdoor environment. They come in a box. But this is the kind of data you want to look for. This is the generator specification for that particular unit. And I've circled the things that are important right here. Radiator airflow. You need to know what the mass flow rate is of that inlet. You also need to know the approximate size of it, which you can usually get from the CAD drawing of it or the cut sheet of it. But you need to know the size and the mass flow rate. That'll determine the velocity. And then on the exhaust side, you need to know the mass flow rate, the approximate diameter or size of the exhaust outlet, and its mass flow rate. So you can see those specs are given here. About 22,000 is normal for an exhaust pipe of a diesel generator. 900 degrees is normal. They generally dump about 122 K CFM for air to cool them. They often look like this. They're in a box. So you see on this one, there's heat inlets or cool air inlets in 2 locations, and then there'll be an outlet on the back. They do vary. The packaging of them varies a bit, and that's why it's difficult to build a single model of these things that represent the entire situation. It's much easier just to make one in CoolSim. And here's an example of how you make one. We have a new object in CoolSim called an inlet outlet. It's just a flat plane. You can set the size. You can see there's one here on the intake. There's an exhaust right there, and there's one on the outtake. So air's coming in through this end over here and being pulled, not literally, by the way. All these are surfaces on a block, so there's no air moving through the block. A common misunderstanding in CoolSim is there's air moving through the block for racks or cracks or anything. There are not. There's just a surface on the front end of it that we set a set of parameters on and do mathematics. This is all done mathematically. So we're pulling air in here, and we're dumping it out here. And the most important one is the dump. The inlet you can set as well for the same parameters. You notice there's no arrow. It's pointing in because it's pulling it in. But pulling in doesn't bother quite so much as the exhaust. The exhaust coming out is hot, so it's running at about 120 degrees Fahrenheit is typical. It does depend on the design, but that's not unusual. And you see here, this one's set for 110. Again, about 110, 120,000 CFM. This one only has one outlet. Some have more than one outlet. This one's very important as well, because this is the diesel exhaust. This is usually about 18 inches by 18 inches. You see I'm represented again as a rectangle. It's actually a round surface. But to save cells in terms of mesh, we model it as a rectangle. And here we have 22,000, again, about the same. We see about 22, 23,000 CFM coming out of that. Temperature upwards of 900 degrees Fahrenheit. That one was set a little lower than that. So let me go back over to my CoolSim for a moment and show you how to build those. So the way those work, let me just back up a little bit. This is CoolSim again. Here's an example of one right here. Now this one has two inlets, one on either side. You can see those inlets, they're coplanar. So, and then the outlet right here. And then there's a block representing the chimney. And then at the top of the block, there's an outlet. And the way to, again, this is a group. Once you've built this, you can actually write it out. You can export it to a file as a CSO file as a group and read it in as a group. You can also save it to your local library if you want. So if you want to build a few of these and put them in your local library, you can. I tend to write them out to a share drive, and that way it's on the network, and if I'm on a different machine, I can grab them from there. So I use share drive for most of my CoolSim work. But let's just ungroup this for a moment and take it apart and see how it was done. Now, these surfaces right here are a little difficult to pick sometimes. So what I tend to do is hide the block. So just hide it for a moment. We have a hide feature, and then you can get at all those surfaces. And you see this one has one outlet over here. This is the outlet. And then these are both inlets where the air comes in, and then it has another outlet at the top. It simply depends on how the original spec was set up. But once you set these, and again, you just click on them and set these parameters to be whatever's necessary. This one you can see has been divided in half at least, so 50,000 coming in. Temperature doesn't matter because it's pulling it, so it doesn't really matter on the inlet. It's only the outlet that really matters. You see the outlet here is probably going to be in the range of 126, and this one's dumping at 109. Probably a little low, but I don't know. It does depend on the spec of the device. So that's how you do that. There are different configurations. Here's an array of condensers up on a roof that I grabbed and wrote out at one point when I was working on a project. Here's a different one over here. You see in this case they had some sort of inlet box. Again, this is just built out of baffles, so you can ungroup this and pull them apart if you want, but that's how that one was built. And again, you can write these out, and once you've built them, write them out and save them and just read them in and use them again in the future, or read them in and modify them and use them in a different style. Very easy to build, and with the copy paste and particularly cloning, it makes it so nice to work with. By the way, we've also added most recently on our group feature, we've added, you can edit the group, which allows you to manipulate it, and you can also rotate that group. So that's a handy feature to have as well in case they're not all lined up the same exact way. So we've added a few features. This will be a growing area for us in terms of capability because this is becoming somewhat common. What we do in CoolSim, by the way, is we typically pull in functionality that we see common. 80%, 90% of the time, if you start to see that kind of frequency of use, you start to say, okay, how do I automate it and bring it into CoolSim and make it something that can be easily used? This is an advanced topic, typically. When I did this kind of work, when we were at Fluent, typically you do all this work by hand, and you hand mesh it, and you hand process it, and you hand post it, and it takes days to do a model of this kind. But with CoolSim now, we're able to do this quickly, efficiently, and do various scenarios in hours. It's really a game changer. Now, setting up the domain. So when you set the domain up, this is, again, the big room. I don't know what you want to call it. The domain, the flow domain is a common way to refer to it. We used to call it a bounding box when I was at Fluent. So this is the size of the domain in which you're operating. Typically, it should be 3 to 4 times the length of the building on the windward side. If you're a sailor, that's the side the wind comes from. Leeward side should be at least 3 times. because we've got to resolve the mesh. The cells, remember, we break the volume up into, in this case, hexes, three-dimensional hexahedras, and then we solve the conservation of mass, momentum, and energy on each surface and interpolate it across the cell, and we have to converge it to an accuracy of typically 10 to the minus fourth. So we're looking for good resolution, and to do that, you need enough size to do it. And then on the top, 3 to 4 times on the top is the height of the building, okay, because it is a three-dimensional block. Now, we've also added in CoolSim some tools to allow you to set the wind condition up. This is normally done in a code like Fluent using unit vectors. If any of you have ever worked with unit vectors, it takes you back to your days of trigonometry and cosines and sines and transcendentals, and it's not trivial. So we came up with a method here where it's got a nice little GUI. So we have a compass and an air indicator. Now, the compass can be offset, because oftentimes you'll lay a model out and go, oh, well, you know, it's not quite facing north. The building's facing northeast. So what this allows you to do is a compass offset. So you can just offset the whole orientation of the room with respect to, or the domain with respect to the building, and then you can set the wind speed and condition according to whatever the prevailing wind condition are for that particular region that you're working on. You can set the velocity. We've got miles per hour. We've got a variety of units here, miles per hour, kilometers per hour, all the rest. You can set the air temperature in a variety of units. And we have a hyperlink to wind data, which takes you to the NOAA site and allows you to look at some of NOAA's data on wind. Now, wind data can be specific to a particular location. So I have a lot of global customers, and NOAA primarily focuses on US data. But there are also local wind roses you can get for your geography as well, wherever you may happen to be, that allow you to understand prevailing wind. Or sometimes the customer will tell you what prevailing wind they want you to worry about, because they have a history with the site. Other cases, you want to pick a particular wind because you know the way you're building and the way your equipment's lined up that you need to worry about a particular wind direction. And if that is the case, then you simply pick the one you think is worst case condition and run under those modes and understand what the probability that that kind of wind would blow and what the impact would be. So the way you do it is just open the room editor, double click on any section of the room, and you'll see now a new feature. This just started in CoolSim 5.1, is this external flow switch. And you hit this button here and it pops this little GUI open, and you can set up your wind environment. And these arrows that you see in the domain are showing the wind direction. So right now it's slightly off to from the east, so it's blowing left to right in this case, but you can set it any way you want. You also have to orient your building with respect to the Earth. So the best way to do this, the way I do it, is to go to Google Earth or Google Earth Pro and open it up, dial in on the area that you want to put your data center. And then, you know, what I did here is just took a cut of the CAD drawing of the data center and laid it into where they want to put it. In this case, this was a consulting project. Make sure the customer is consistent with that's yes, where we're going to put it. And then find north using Google Earth, and then find out what your approximate orientation of the building is to north. You're going to need to know that. The other piece of information you're going to need to know, if you don't have a prevailing wind already in mind, is setting up the simulation domain. So in terms of wind speed and wind velocity. This is a windrose. I don't know how many of you know a windrose or what it is. I thought I would just show it to you. This windrose shows us the probability and strength of wind. So you can see that the wind is, 10 to 14 miles per hour occurs at some interval. That's probably the worst speed, but it only occurs, a percentage of the time. In this case, we've got about 6% of the time. We've got a wind blowing from the east. So if I were to, and over here we've got a little red, so that means we're up to 15 miles an hour on the west, and that occurs some percentage of the time as well, 4%. So if I were modeling this data center, I'd probably want to take a look at wind from the east and wind from the west, maybe offset them a little bit to understand what the impact is. I mean, most of the time this place is calm, but you do have some wind conditions, and this happened to be Phoenix. Examples of layout. So this is a typical data yard I pulled from a model that I was working on. I, protect the innocent by not telling you where this is, but you see there's quite a bit of stuff in the, and by the way, it's almost always surrounded by a perimeter fence. Perimeter fences cause problems because they create pressure variations on the back side. So doesn't the building. So we've got this block sitting here that is problematic. If the wind blows from this direction, it's going to hit that block, and it's going to create, an area right here where there's accumulation of heat, most likely. If the wind is blowing in this direction, it's going to take the heat from these generators and move them down into these cooling arrays and cause issues down there. If the wind is blowing hard in this direction, right over the leading edge of this fence, you're going to have a low pressure area. Or in this direction over the leading edge of this block, which is the building edge, you're going to have a low pressure area. But that's my experience, by the way. I can stare at these and understand what the worst case condition might be, but that's experience. What you'll want to do most likely is experiment and run and get a feel for what that building looks like as a function of wind condition and wind velocity. It can be a little tricky. Sometimes low velocity winds are worse than high velocity winds because they create some pressure gradients that may not be there if it blows a little harder. This is another representation. In this case, the diesel generators are inside a building, and there's an exhaust squirting out the top and an intake pulling in below it, or exhausting. It looks like exhausting below it. So I don't know where the intakes are here. They might be somewhere else, but these look like they're exhaust, and that's the exhaust pipe. And then, of course, you've got all the heat exchangers and chillers sitting up on the roof. So this one could be problematic, particularly with a wind that's moving in this direction, perpendicular to that surface. It may blow this hot air up over the ledge, over the edge of this top building, and contaminate the leading edge of these devices. Another example here. Now, in this case, there's some structures in front of these heat exchangers. I think the goal here was to get these further back on the roof so that they're not being contaminated. This is the same variation of the same design I showed you before. The generators are down here and they're blowing heat up over this edge. It's okay to have other stuff up there, but let's keep the heat exchangers as far away from that hot air as we can get. So I'm going to give you some examples. Let me check the time, 10:28. Okay, we're making good progress here, and I haven't been looking at my questions. Is the CoolSim software a modeler and a solver? Yes, it is. It does both. We both create the model and solve it. That's the point, and I'm going to show you some solutions here. And the mesh is automatic. We automatically mesh these. So all you do in CoolSim is once you set this thing up, you press the go button and it meshes. And we use meshing technology that is from ANSYS. It's all ANSYS stuff, the state of the art. Latest ANSYS releases is what we use in our solve, which allows us to ride that technology curve and deliver those solutions to you very, very cost effectively. But we do it for you, and we do it based on experience we have in meshing, which some 30-odd years of experience in meshing. So we set the meshes up and run them for you. And if it fails, then you'll get a failback, and we'll get copied on that fail, and we'll help you debug it. So that's how we do it, and that improves the pipeline over time for others so that, yep. Okay, so let's take a look at some results and keep asking questions. I'll keep trying to look over there and answer them as we go. So here's an example of entrainment. Now, one of the nice things about CoolSim is we give you hyperlinks to output. So when you run a job, you not only get the solution done and you get to look at it locally, as always, but you also get this hyperlink capability, which allows you to open and view it on the internet. Now, this is a wonderful thing and something I've been trying to do nearly all my life in 3D graphics, is to be able to view results, for example, on your phone. I can see this on my phone. In fact, I can send this to you as well. This is another wonderful thing that we have here. In the chat box, I can dump this URL, and you should be able to, nope, I didn't get that right. Oh, maybe I did. Oh, this is local. In any case, you should be able to view these results. Maybe the next one. I don't think that URL is quite right there for that particular. In any case, let me show the results and we'll share the URL later. But you see here that over in this section is what we call the numerical data. So this tells you what your offset was, and the temperature of your flow, and the velocity in the room. This is actually room dimensions. You should say domain dimensions, actually. And it also gives you an independent report of the analytics of each one of the I/O devices. So here's the generator, and it's got inlets and outlets, and it's got temperatures. You see the exhaust is flowing at 700 Fahrenheit, and the exhaust of the heat exchangers themselves is running at 118. So this is all the analytical over here. Here's the HDUs dumping heat. You can see they're running at about 17,000. We've got a delta T of about 14 degrees there, and we're dumping 68 kW per entity. But the most sort of revealing is this one down here called path lines. Path lines from racks and PDUs. It's actually, should say, HDUs at this point. Again, this is a new release, so these things are growing. But here's an example of flow on a prevailing wind coming from those devices up on top. So in this case, we have a bunch of these heat exchangers sitting up on the roof of a fairly large data center. And you can see as the heat comes out and the wind blows by, we get these various effects. Let me show them to you. Again, this is ANSYS technology I'm using, but we provide it here as part of CoolSim, and allows you to see these path lines. So what's happening is that as the air goes by and gets to this back edge, it pulls it down because there's a pressure gradient right there. Whenever wind flows over what we call a backward-facing step, you get a gradual temperature pressure variation right here that causes that to pull down. You often see this. This is why the back of your car is always dirty in the wintertime in New Hampshire, is because you got a low pressure there, and as the slop goes by, it wants to collect and swirl right here. And that's what we're seeing. We're seeing this heat come out of the top, and instead of going up into the atmosphere, some of it's pulling down and getting entrained into the rest of those heat exchangers. And that will cause their performance to decline. So it happens in the windward direction. It also happens side to side as well. In some cases, you'll see them going from one to another, just wrapping down around and going into the one beside it. So this is the problem. This is what we're trying to solve, and you see it going way down underneath. And then what you say is, okay, what do I do to solve it? Well, just like in hot aisle, cold aisle containment, yeah, you can see them going down right there. See how that one goes right down underneath? This is a very common thing that I see, is the exhaust gets sucked into the intake. The reason for that is the intake, of course, is running at a lower pressure. And the other reason for that is usually a screen right here, which there is in this case, and that screen is causing a low pressure on the back side of it. So down low near the surface of the roof, you've got a lower pressure than you do up on top. And what that does is tends to pull the air from the exhaust down into the bottom. So they just recirculate on themselves, causing efficiency to drop off quickly. A couple of ways to solve that. One, you could put a block right across here, like a steel platform that didn't allow air to pass through it, and that would block, much like we do inside the room when we do hot aisle, cold aisle containment. Similar idea. The other thought is to extend these up with chimneys. You can push these up further into the air, causing the distance between the exhaust and the intake to just be further apart from one another, thereby reducing the probability that that'll occur. Now, those solutions I just described come with cost, and you have to discuss those with your customer, but that is what would prevent it. Now, in terms of showing you the impact of that, there is a plot right here that we added in version 5 called HDU inlet average temperature. And this is really the most important plot probably in this set that you see here. There's a bunch of temperature contours I'll show you in a moment, and velocity contours if you want to look at those, and also some other elements here. But this is one of the more important ones, the HDU inlet average temperature. So here, it takes a while to build that because it's made up of a lot of very, very small elements. But let's take a look at this closely. So I'm going to use a control key here called a Y to put it into, and the wind, by the way, is coming from the right to the left. I'm going to turn perspective off. And again, I can share this. I'm going to share this one with you. So copy. I'm going to go to the chat and to the entire audience, type my message here, Control V, and see if I can. Yeah. So now in the chat box, you can click on the hyperlink and you'll see this image pop. The reason I'm showing you that is this is an excellent way to share 3D images with your customer or your prospect or your colleague. You can do it with hyperlinks. You can do it with your phone. You can share with your phone. by forwarding a hyperlink. This is a hyperlink of this particular image. I zoomed in on it, used a Y key to orient it so that it's facing straight up. Y is upward vector in Fluent and then CoolSim. And you'll notice that as the wind is blowing from, in this case, I believe it's angled, so it's definitely coming from the right-hand side, and it's blowing this way. You can see these are fairly cool. But as you get here, they start to get red. So the performance of these heat exchangers over on this end of the array is going to be very poor. Their inlet temperature is upwards of 143 degrees. The temperature, the ambient air temperature, is around 100 in this day. They're modeling it at very high. Again, you look for the corners of your design, what we call the four corners. In this case, high temperature, worst wind condition is what you want to model to understand, in this case, what your cooling, your aggregate cooling capacity will be on a given day. You can calculate it by understanding what that average temperature inlet is, and then determining what the efficiency of this heat exchanger is with an inlet temperature of 143 degrees. Or conversely, how hard your chiller's got to work to pump up or to boost or to lift the pressure in the compressor high enough so that the cooling medium is well above 143 degrees. So this is not a good picture. You want to try to avoid this. We call these Visine charts. Get the red out. You know, you got to get the red out of the image, right? So a couple questions coming in. Can the 3D path line be constrained to show only a section of the model? Yes, it can. What is the effect of the screen on those chillers with respect to the wind? The screen, you can adjust the percent area open on the baffles to represent percent area open on screens, so you can model that. What would you take to considering the windrows of different probability of wind? Consider the maximum speed, which is the maximum. Well, you can consider a lot of different things with the windrows. The windrows just simply gives you an idea of what to look for. It is a discussion with the customer about, you know, at the end of the day, what they're most interested in. It often has to do with the orientation of the building and the location of these devices with respect to the building. So in this particular model, you've got all of these generators sitting out here, yet we're looking at a wind coming from, in this case, the right-hand side. That's because it's the prevailing wind. But another study I would want to do here is this direction. Do these generators contaminate these heat exchangers under a wind that's coming from the top side? That would be a study you want to do. To redo a study, all you need to do is just reset the model, change the wind directions, and resubmit it. Turnaround times on these models tend to be a couple hours. I was turning this one around in 2 hours, so that's not too bad. It does depend on the mesh. The mesh in this case is 15 million cells. We ran it on 8 cores. So that probably took a few hours. By the way, CoolSim is automatically parallel, and you can run concurrent jobs at the same time. So that entire model meshed at 15 million cells on 8 cores. We use about 1 million cells per core on average, and we just keep adding cores until we have enough to meet the needs of the mesh. We do that all fully automatic. You don't have to, as a user, worry about that. So change is made. So here's another image. This is the same one, and here what we did is to simply put a plate in place. So here's the same model, but here we put a plate. You can see it right there. The plate separates the hot and the cold from one another so that you have less reentrainment, and you can see there's less here. So where before, let me just hide this body, right? Hide that body. So where before we had air coming down and going under this section really quickly, and let me rotate this a little bit so you can see it a little bit better. Where before we had the air coming down and being pulled underneath really quickly, here it's not so bad. So same exact conditions. We've made a change to the geometry, put a plate in place. This is a separation plate between the hot and the cold. Now that's expensive because that doesn't have any percent area open and you've got to worry about water. So you might want to put a perforation on that. I can't remember if we perforated it or not, but putting a plate there will reduce it and improve your total outcome. And then it becomes a question of cost. Is this something that is cost effective? Is this something that the customer wants to do? What is the probability it's going to happen? These are all decisions made in the design process. And this is simply a tool to allow you to make better engineering decisions. That's all CFD does for you, is essentially give you more information from which you can then make decisions. But you can see this one cooled off quite a bit. Now, this is in centigrade. Sorry, I have to flip that switch to centigrade, but you can see there's and the range is the same as before. So this is about, up here is about 143 degrees Fahrenheit up here, and you can see there's fewer of them. The temperature gradient is further back. That in general, we got improvement. Now, whether that improvement was cost effective compared to the cost of the implementation, that's a good debate that you'll have with the design team. Furthermore, we didn't implement chimneys here. You could try chimneys as well as an alternative. That might be more cost effective. I have seen that in some cases being most cost effective. So that's one I wanted to show you. Another one here, and again, these are all hyperlinked shots that I'm able to just pull up because we support hyperlinking on results now. So I'm pulling this right off the cluster, and we're watching it in real time or manipulating it in real time. And you can do this from the comfort of your home. You can do this using your phone. And it is the first time that I know of that that's been able to be done, particularly on this complexity of a problem. So here we have rooftop air handlers. Again, I wanted to show you some of the re-entrainment that occurs. Now here, there's chimneys that have been put on top. So this comes a little bit later in the cycle than prior. But what we're seeing a lot of here is re-entrainment right from the exhaust into the intake. And you can see chimneys have been added. In this case, the chimneys are made using baffles, 4 baffles, and then cloned. You can also simply make your HDUs taller so that the outlet is up higher that mimics the effect of a chimney. You can do it either way. I tend to extend the height of the HDUs a little higher to mimic the effect of the chimney, effectively giving these more room to go out into the atmosphere before the low pressure starts to pull them in. So that's a nice shot of what's going on there. Again, if we look at the HDU plot, which is this HDU average inlet plot, which is one of the more important, we'll see here that there'll be most likely you see some heat being generated there on that side due to the wind blowing over this direction, and there's probably heat coming off these devices. Now, we do separate the path lines here so that's a little easier to see. What I was showing you earlier is just the path lines from these devices. Let's go now look at the path lines from the generators themselves. They're down here in the velocity inlets by temperature. So these are just the velocity inlets themselves. And you can see here on this output that there is quite a bit of heat coming off those generators. In this case, these are the exhausts right here for the diesel generator itself. You can see those are running near 200 degrees Fahrenheit. And then here is the exhaust from the generators themselves blowing out the front. And you can see it gets wrapped up over the front of that. So let's see if we can, there we go, and turn off. I'm using keystrokes here. So I used a Z and an N. And that's a pretty good shot right there of the problem. So as the wind blows, it causes this heat to come up and bang off that surface right there and get up into those intakes. And that's what's going to cause a few of them that we just saw to be hotter than they should be. So then you say, okay, there's the problem. I see where we are. What can be done to eliminate it? Well, the first thought is to put a screen around it because that's normally what you do anyway. So I believe in the next run, I did that. So let me put this run down and then go here to this one and take a look at this output. And you'll see if we take a look at the same plot. And by the way, these plots can now, these hyperlinks can be hidden underneath PNG images and put into a PDF report. So you can make all of your images now that you deliver to your customer full 3D by simply hyperlinking the PNG or the JPEG or whatever it happens to be that you have. Put the hyperlink behind the image, and that way when you deliver the PDF to them, they simply click on the image, and if they're not tied to the internet, a browser pops open and a 3D image comes up, and they're able to manipulate it themselves. This is a beautiful way to make reports, and again, something I've been trying to do most of my life. So here we have percent area open set on that front screen. They usually are, and you can see it's still blowing through it. It's probably better than it was, but these screens tend to cause some of their own problems. As I mentioned, they create a low pressure inside them simply by the fact that you've got flow over the top of it, and when it goes to the other side, it creates a low pressure. But put a screen around it, and let's take a look and see if our HDU temperatures dropped. These are the condensers, the heat exchangers. And let's see. Yeah, you can see it helped. It helped. It brought them down a little bit. So now we're down in the 120s. It did help. And again, how much it helped is a function of cost. You know, is it cost effective? So CoolSim doesn't talk to you about cost effectivity. Looks like we got an outlet wrong there. You can see it right there. That's not correct. On the post, in the post, it posted an incorrect outlet right there. But yeah, you can determine the impact, and then the cost is something that has to be studied dependent upon the situation. So that's the kind of thing we do. In summary, we're getting here close to the top of the hour, and I want to leave it open for questions. There's a few here I haven't gotten at. And so they can be constructed fairly easily with blocks and baffles and I/O objects. And then once they're created, you can group them, which is the same as an assembly, and then save them, and then clone them, or rotate them, or do other things with them. You want to be sure that your objects are set up to reduce as much mesh density as possible. You need to align them as perfectly as possible. You would like to, for sure, be able to get your inlets and outlets to match the block size. So let me just take you there again, and we're going to pop CoolSim for a moment. I want to make that point. So in making your inlets and outlets, and I'll use this image again, try to make them, try to make the outlet as close to the size of the block as you can. You see it wasn't done right there. Whoops. So here you see how the inlet, in this case outlet, is not quite the size of the block. You should make it the same size of the block so the mesh doesn't have to do a double mesh here. You're already meshing this surface, but you'd also need to mesh this surface as well independently, and that's a very small geometry for a room of this size. Now, with respect to these on the side, same thing. Try to go to the edge if you can. So you see this one is just about near the edge, but you can see there's a gap right over here that you'd like to stay away from. So this one should have been done with the dimension in this direction equivalent to the size of the block, and bring it right to the edge if you can, if there's not another inlet there. And in that case, there's not. So I would have made this one the width of the block, and I would also bring this I/O device, this, in this case, outlet, up to the edge so that you don't have to mesh that surface around it. You'll see that's what we do on our regular structures like this one, like the PDU here or the HDU. You see that outlet is equivalent to the size of the block. So that's the kind of thing that you want to do. It's not imperative, they still work, but it's just meshes a little bit better if you get them lined up perfectly. In a case where you've got them on either edge, you do need to leave a gap. For example, in this case, we had to leave a gap between those edges because you've got an outlet there and an inlet here. And if they touch, then it sometimes causes that solver to get a little confused about which is which. So we've had to, in this case, leave the gap right here on that leading edge in order to keep them separate from one another. So just a couple of tricks about how to build good structures. So, yep, the main size should be about 3 times on the windward side, 3 to 4 on the leeward side. Height of the domain should be about 3 times the building. Run them on course. We've got enough mesh. The course mesh setting on CoolSim is the most robust. That's the one we've spent the most time on in terms of optimizing it, and it will give you the best output. Runtimes on these jobs tend to be 3 hours, 2 to 3 hours for a job. If you have other questions, you can reach me at this email address, and at this point I'm going to go over to the question board and just start answering some of the questions here. Option to calculate the correct flow rates in technical rooms with condensers units. Yes, of course, you can set those condensers up any way you want. You generally use the spec sheet from or what's called the cut sheet from the supplier to get those set up. If you have any questions, just reach out to us about that. Is the CoolSim modeler in a solver? Yes, it does. You don't have to have a separate software for each. It does it all. It's a one-stop shop. It is a system. You just build the model and submit it. How do you provide a mesh to the models you've created? We automatically mesh using the ANSYS hex dominant mesh, same one they use in IcePack. Technical rooms are closed, so they have a roof, and the only exhaust will be the right and left sides. Yeah. Well, you're talking about the domain. The domain itself has outlets on either side. The top is considered a wall. The floor is considered a wall. So yes, you are right. It can exhaust out of, it can come in on one side of the domain and go out on any other of the three walls. We don't include an exhaust at the top or an outlet at the top of the domain because it tends to confuse people too much because you see the flows drifting up to the top. So we switched it to a wall, and that seems to be working fairly well because the area of interest is near the heat exchangers, not the far domain condition. What would you consider taking the wind rows, the different probabilities of wind? Yeah, I mean, picking the wind speed, and the direction is an iterative process that you go through based on staring at the wind rows, talking to your customer, and determine how many variations they want to perform. Variations cost money because not only are we computing, but we're setting the model up, meshing it, and getting it to solve, and that does take time. Or you have to have a CoolSim license, and we support you through that process. So variations do take time. Someday in the future, we'll be able to run all n variations at once and have it tell you where the problems are. but we're not quite there yet. We're still trying to get these to solve automatically with good results and good robustness. Let's see, visualizing the horizontal containment. Long roll of heat exchangers won't supply air into the heat exchangers reach starvation fairly quickly in the row. Would organizing the heat exchangers in V's of diamonds relieve some of that low pressure pulling that containment down? Yes, a little. Remember, you can always model these things to higher levels of fidelity. You can model the V structure and do it that way as well, but your meshes will be huge. Your time to solve will be extremely long, measured in days, and you're going to have to be in that loop doing manual post-processing. In other words, what the CoolSim tool does for you is help you eliminate bad ideas as well as promote good ideas. It is not an analytical tool for determining temperature T at a point in 3D space. You can use CFD for that, but it takes a lot more time in detail and mesh density and computational capacity to get temperature T in a three-dimensional space. The best use of tools like this in the design process is the elimination of bad ideas. I want to put the heat exchangers all here. Well, that's not going to work. Why? Let me show you why. And CoolSim can give you very quickly answers to why you don't want to do that, or that it's better to put them over here. And that's the answer you want, is what is best. Should I put them here or should I put them there? Doing the detailed geometry of the shape of the inlet of the heat exchanger is not relevant to that conversation, because at the end of the day, you'd still be comparing placement of position A to placement of position B. And you will have done all that meshing and solving and posting and fooling around by hand, only to get to the same conclusion. So the detail that is exposed in a computational fluids model should only be sufficient to answer the design question of, is this better than that? Which we always kidded can be, you know, the funny part is we generate all this output data for a question that is either a yes, no question. It can be answered with one bit, 0 or a 1. Does it pass or not? And that's the answer you're looking for. If the wind is considered coming from the north side of the image you were showing, are you looking for generation containments and entrainment inside the building? What is the effect of contaminants you see on the chiller? Again, more detail. Contaminants, I think your thermal contaminants in this case. What are the contaminants you see on the chiller? So again, this is a level of detail that allows you to do comparisons. If you want to get into the details of what's going on inside the chiller, you have to model the interior of the box. You can do that, but your mesh count's going to grow, your complexity is going to go up, and you can't solve it in a domain that is, several hundred feet in one direction and several hundred feet in the other direction, or 1,000 feet, and then a height. It's computationally too expensive. So what we do in this business is we try to build models that are representative of the real world, and keeping in mind that it needs to be done in a reasonable amount of time. If you've got the time, you can use Fluent and take the model from CoolSim, bring it into Fluent, and do all the work there to add a higher level of fidelity. But at the end of the day, you've got to get it done in a certain amount of time. So cost effectivity in terms of time and human labor is an important consideration of these kinds of tools. There is a question about cost of the software. Our software here's costs. The entry point for CoolSim is $9,000 for an annual license, occasional use license. We're assuming you're going to use it there a certain amount of capacity. We don't restrict it, but we do have assumptions about how much you're going to use it. So we do have monthly as well, but I have a lot of users using, most of my users are $9,000 annual occasional use kind of license. If you advise on modeling the crack and racks within the data hall together with the outdoor condenser. Yeah, well, man, you can start to build it bigger, more complexity. It'll take longer to solve. It'll be more complicated. It's better to do them as submodels. Submodeling is the idea of taking a section of your problem and modeling it to understand it, and then doing another section and then comparing them. Some of the models we've tried to build in CoolSim are just too big. We've done a few lately in external flow that are 50 million cells. And it's not that they weren't lined up perfectly, they were. It's just that there's so much complexity. There's so many condensers, the building is so large. And so in that case, what we do is submodel it. You basically slice it in half. This is very common in simulation to do a slice and then assume symmetry that it's going to be the same. We do this in aircraft engines all the time. You use symmetry because it's impossible to model the whole 360 degree of an aircraft engine, things like that. So symmetry is something you use, and submodeling is something you use as well. What I would do is model the interior first, understand how that behaves itself, and then go to the exterior. Now, someday, it could be that we're able to do it all at once, but and computational capacity is doubling every 18 months and has continued to do so. So I'm hoping that someday you can model the whole thing very quickly, as I am also hoping that we can consider all wind conditions and wind velocities in a single model. But until that happens, we have to make approximations, and we have to use a reasonable amount of time with respect to computation. And CoolSim does that very, very well. So external implications of heat exchanger placement, efficiency, influence of the positioning of high-density compute nodes inside a data center. Yeah, it all has an effect. I mean, but do the inside separate from the outside. There are two different models at this point. Model the interior, understand what's going on in there, understand how much heat you're going to dump, and then go to the exterior and find the optimal location of these devices in the outdoor air within the bounds of cost, within the bounds of a customer's appetite for placement. Customers can be fussy. They don't want to see the heat exchangers, or they don't want them too far forward on the building, or they want them further back. Aesthetics are often a big component of the overall design from the point of view of the customer. Our job, collectively, you and I, is to figure out what's the best placement in terms of thermal efficiency and still meet the aesthetic desire of the customer. So with that, we're at the top of the hour. I like to try to keep these to an hour. I want to thank you all for attending. There will be a recording of this as well that you'll be able to access. If you have any questions or want to follow up, please send me an email and we can talk about it. Thank you everyone for attending today. I greatly appreciate it.